We present Deep Global Registration, a differentiable framework for 3D pairwise registration. 3D registration is a process of finding a spatial transformation that aligns two point clouds, and it has been studied widely for reconstruction, tracking, and pose estimation. The first family of works finds local correspondences and optimizes pose. Others use branch and bound or random sampling for globally optimal solution. Recently, learned models have been proposed for 3D registration. Wang and Solomon proposed a 3D registration network with Procrastals, which requires quadratic complexity. Aoki et al. Used global features for iterative pose optimization, but this results in coarse spatial resolution. Our pipeline starts with feature matching. First, for feature extraction and matching, we use FCGF, fully convolutional geometric features. We densely extract FCGFs and use the nearest neighbor in the feature space for matching. However, not all correspondences are accurate, and we filter out the outliers. Let XYZ1 and 2 to be a correspondence. Some correspondences will satisfy the transformation equation, while others don't. Choy et al. Showed that ones that satisfy the equation are inliers, and they form a 3D subspace in a 60 space. In other words, the inliers form a geometric structure while outliers will be noise, and we frame this as a foreground segmentation problem and use a 60 column-net to segment the inliers. Next, we find a transformation that minimizes an error between a correspondence. If we use a squared loss on a set of correspondences, we get Procrastals analysis. However, it weighs all correspondences equally, which is not valid in most cases. Instead, we can use inlier probabilities and use these as weights and show that it has a closed form solution. And we can pass gradients through the weights. We name this Weighted Procrustes, and it has a couple advantages. First, as we pass gradients through the weights, the complexity is linear to the number of correspondences, which allows us to process many correspondences efficiently. Second, we can assign 0 to the weight and effectively remove correspondences, which is critical when we have regions with no overlap, like the highlighted parts. Lastly, the fine-tuning model uses a robust loss function and optimizes the pose using SGD. For continuous rotation representation, we use the orthogonal representation proposed by Zhou et al. In sum, the pipeline first starts with feature extraction and matching, followed by a 60 column-net for inlier probability prediction. Then Weighted Procrustes converts these to a 60 pose, which we optimize further using a robust loss. However, when the number of valid inliers falls below a certain threshold, we use a time-consuming but inaccurate registration method. We train and test our method on the 3D Match benchmark. The 3D Match benchmark is a collection of 3D scans of indoor scenes for 3D reconstruction and has been widely used for feature matching and registration, and it contains a lot of challenging scenes with low overlap. We use the registration recall as our main metric, which measures the number of successful registrations. First, note that the latest learning-based algorithms that require almost complete overlap fail on the 3D Match benchmark, since many pairs have a small overlap. Next, ICP variants including point-to-point and point-to-plane achieve about less than 10% recall. Globally optimal ICP variants, including GoICP, achieve around 20% recall. FGR and RANSEC achieve better performance but are below 75% on average. In this difficult dataset, our method achieves a significant performance improvement, and it reaches 92% registration recall. When we compare our method with FGR and RANSEC, we achieve better alignment on small objects. We highlight the registration misalignment of each method in red boxes. We also show that our method outperforms all baselines on wide range of rotation and translation thresholds. In addition, we plot the speed on x-axis and recall on y-axis of all methods in this plot. Compared with other methods, ours get a better performance while achieving median speed. We also apply our method on a multi-way registration framework. This is the visualization of our multi-way registration result on the LiDAR RGBD dataset, apartment scene. Similarly, this is our registration result of an office scene. In addition, we use the outdoor LiDAR scans from the Kitty dataset for pairwise registration. Please visit our GitHub page for more information.